standard 3072-bit RSA key against a 256-bit ECC key. In NIST's security tables, these two provide an equivalent security margin, despite the ECC key being less than 1/10 the size. RSA relies on the integer factorization problem, but because researchers have developed sub-exponential attacks against it, protecting data requires increasingly longer keys. Properly chosen elliptic curve groups do not have comparably fast known classical attacks. To understand why ECC is more robust and how hidden backdoors are engineered into its parameters, we must first deconstruct the underlying geometric group law. The security of modern communication depends on the ability to translate these elegant geometric curves into a discrete mathematical fortress. This is an elliptic curve in the short Weierstrass equation form. Plotted over real numbers, it forms a symmetric structure where every value of x corresponds to both a positive and negative value of y. For cryptography, we must define a unique method of adding 2 points together on this curve. The result must be a third point that also exists on the curve, satisfying the axioms of a mathematical group. If we select 2 distinct points, P and Q, we draw a secant line through them. Because of the curve's cubic nature, this line will intersect the curve at exactly one other location. To find the final sum, we reflect that intersection point across the x-axis. This resulting coordinate is point R, the geometric sum of P and Q. When adding a point to itself, we cannot join 2 distinct locations. Instead, we draw a tangent line at point P, find where it meets the curve, and reflect that point to find the result, 2P. If 2 points are vertically aligned, a line connecting them will never meet the curve again in standard Cartesian space. To complete the group, we define an identity element, known as the point at infinity. This method of geometric addition ensures that every operation loops back into the curve, forming a closed system required for cryptographic security. While continuous curves are useful for visualization, computer processors cannot operate in continuous space. They require discrete, bounded integers. To make the math executable, we move from real numbers to a prime finite field using modulo arithmetic. The continuous line shatters into a discrete scatterplot of coordinates bounded within a modular grid. Even in this discrete space, the same geometric rules apply. When we calculate the line between 2 points, the modular arithmetic causes the path to wrap around the grid until it strikes a third discrete point on the curve. This allows us to perform scalar multiplication, adding a base point, g, to itself a specific number of times to generate a public key. This creates the elliptic curve discrete logarithm problem. If an attacker sees your final public key, it is computationally impossible to determine how many times the base point was added to itself to reach that coordinate. By porting geometric logic into modular arithmetic, we create a one-way function that resists the attacks currently threatening RSA. This math allows Alice and Bob to establish a shared secret over a public channel through the elliptic curve Diffie Hillman, or ECDH, handshake. However, not every point on a curve is equal. Every point generates a subgroup, and the ratio between the total curve size and a specific subgroup is called the cofactor. Resource-constrained IoT and embedded devices often skip this step of validating these subgroups to save processing power and memory. In a subgroup confinement attack, an adversary sends a malicious public key that exists only within a very small subgroup, perhaps one with only 7 points. Because the device skips validation, the resulting shared secret is forced into that tiny subgroup. This limits the possible keys to just a few values, allowing the attacker to guess the secret and extract the private scalar bits. Mathematical security is neutralized when an implementation prioritizes speed over the rigorous validation of geometric properties. These algebraic structures can also be weaponized to create backdoors in pseudo-random number generators. The 2013 Snowden leaks revealed that the dual EC-DRBG standard contained a deliberate backdoor allegedly engineered by the NSA. The generator relied on 2 base points, P and Q. The vulnerability existed because Q was secretly a specific scalar multiple of P. By knowing the secret scalar E that relates Q to P, the creator of the curve can bypass the discrete logarithm problem entirely. An attacker knowing this relationship only needs to observe a few bytes of output to run the generator backwards and predict every future encryption key. A standard can be mathematically valid on paper while being compromised at inception through the manipulation of its starting parameters. Similar vulnerabilities exist in digital signatures, which are used to prove identity and ensure that a message has not been altered. This problem was first identified in the original RSA algorithm, where signatures are computed using large integer exponents. RSA signatures are naturally subject to multiplicative homomorphism. If an attacker has valid signatures for two different messages, they can simply multiply those signatures together to forge a valid signature for a new third message. To prevent this, modern systems use the hash-then-sign paradigm. The data is processed through a cryptographic hash function before the signature is applied. The hash destroys the algebraic structure of the message. It ensures the mathematical relationship between two messages cannot manipulate the final signature. By intentionally shredding the message structure, we ensure that attackers cannot use the rules of the algorithm against the system itself. A mathematical proof exists in an ideal space, but its security degrades when it encounters the hardware and software constraints of physical network deployment. The geometric group law provides a powerful defense against classical attacks, but the complexity of these operations introduces a new level of fragility. A single skipped validation check or a maliciously selected starting point can neutralize the security of the entire curve. As we transition into hybrid post-quantum systems, the integrity of our cryptographic parameters will become the deciding factor in our long-term security. While the math of elliptic curves is sound, cryptography is an engineering discipline where every parameter and line of code must be rigorously verified.